The analysis of beams with one or more internal hinges. A video version and a written version of this presentation are available at the links given here. When designing structures, it sometimes becomes necessary to connect two shorter structural members to form a longer one. Such a connection, also called a splice, can be classified as either a moment connection or a shear connection. A moment splice rigidly connects the two members such that an internal bending moment as well as a shear force develop at the joint. In contrast, a shear splice allows relative rotation between the two segments and is less rigid than a moment splice. Consequently, no bending moment develops at the shear splice. The connection acts as an internal hinge, transmitting a shear force only. This diagram shows the internal forces associated with the two connection types. In the case of a moment connection, we have a pair of shear forces and a pair of bending moments at the splice. In the case of a shear connection, only a pair of shear forces is present. Bending moment at the splice is 0. Herein, we refer to a shear splice as an internal hinge. In this lecture, we're going to focus on the analysis of beams that embody one or more internal hinges. Consider this beam. It is fixed at the left end and rests on a roller support at the right end. Furthermore, there is an internal hinge at point C. According to the free body diagram of the beam, there are 4 unknown support reactions. There are 3 unknown reaction forces at the fixed end, and there is 1 unknown force at the roller end. We can write 3 equilibrium equations for the entire structure. However, these equations are not enough to determine all the unknowns because there are 4 unknowns and only 3 equations. Does this mean the structure is statically indeterminate? This would have been the case if there was no internal hinge in the beam. But the presence of the hinge at point C makes the structure statically determinate. That is, we should be able to determine the support reactions solely using the static equilibrium equations. Here is how. First, we separate the beam into 2 segments at point C. Since no bending moment is present at the hinge, we get a total of 6 unknown forces for the left and right beam segments. Furthermore, since we can write 3 equilibrium equations for each segment, we get a total of 6 equations. Since the number of equations equals the number of unknowns, the beam is considered statically determinate. Therefore, we can solve the equations for the unknowns. Here is the free body diagram for the entire beam. And here are the free body diagrams for the 2 beam segments. Observe that the internal shear force at the hinge is drawn on each beam segment. On the left segment, the force is shown to act downward. On the right segment, the force is shown to act upward. These 2 arrows must always be drawn in opposing directions like we have shown here. Also note that I have placed an internal axial force at point C. Although most beams do not carry such a force, for completeness purposes, we need to show the force on the free body diagram. Similar to the internal shear force, the internal axial force at point C must appear in a pair, acting in opposite directions. The equilibrium equations for the left beam segment are. For the right beam segment, the equations are. Solving these equations simultaneously for the unknowns, we get. Here are the computed support reactions drawn on the beam. But what if the beam has multiple internal hinges? How do we analyse it? Here is a beam with 2 internal hinges, one at point E and the other at point F. The beam rests on 4 supports, a pin support at point A and 3 roller supports, one at point B, point C and point D. Therefore, as shown here, the number of support reactions is 5. Note that the two hinges divide the beam into 3 segments. If we cut the beam at the hinges, we get these free body diagrams. As you can see here, we are introducing a shear force and an axial force at each cut point. The internal forces at joints E and F, plus the support reactions, give us a total of 9 unknowns. Since we have 3 beam segments, and we can write 3 equilibrium equations for each segment, we get a total of 9 equations. Given that the number of equations is equal to the number of unknowns, the beam is considered statically determinate. The equilibrium equations for segment AE are: for segment EF, we get these equations. And for segment FD, we have. Solving these 9 equations, we get the values for all the unknown forces. The results of the analysis are reflected in this diagram. As we just demonstrated, when a beam has one or more internal hinges, we can analyse it by dividing the beam into multiple segments at the hinges. Then we write and solve the equilibrium equations for the segments in order to complete the analysis of the beam.